While most planets spin somewhat sideways as they orbit the Sun, Uranus actually rolls vertically along its path like a ball. Because of that extreme 98-degree tilt, the planet's hemispheres are forced into extreme alternating seasons, decades of continuous, unbroken daylight, followed by decades of pitch-black darkness. In 1986, after a 9-year journey, NASA's Voyager 2 probe finally arrived to get our first close-up look. The probe had just about 6 hours to gather data as it flew past, but instead of clarifying how this distant world worked, the measurements it beamed back contradicted almost every existing model of planetary behavior. That single brief flyby left researchers with a puzzle that took nearly 40 years to solve, as the measurements simply didn't align with our established laws of physics. The first major contradiction involved the planet's rings. Unlike the sprawling disks of dust and ice seen around Saturn, the rings of Uranus are incredibly thin and stay tightly confined to remarkably narrow lanes. This happens because Uranus is surrounded by tiny satellites called shepherd moons. As they orbit alongside the rings, their gravity plays a continuous game of ping-pong with the debris. If dust particles drift too far outward, one moon nudges them back in. If they drift too far inward, another moon pulls them the opposite way. It is an intensely chaotic environment, as seen on the moon Miranda. Despite its incredibly small size, its surface is covered in deep geological scarring, featuring sheer cliffs that drop up to 20 kilometers straight down. Given all this orbital activity and decades of extreme sunlight, scientists expected the planet to host a violently active, stormy atmosphere. But when Voyager pointed its cameras at the surface, it found a pale, featureless blue sphere. There were no visible weather systems at all. This eerie calm is the result of a dead planetary core. Giant planets typically have active interiors that generate massive amounts of heat, fueling atmospheric storms. But Uranus's core generates almost no heat, leaving its atmosphere with very little energy to work with. While a cold, inactive core explains the boring weather, it makes the next piece of data Voyager collected physically impossible. In planetary physics, there is a simple rule. To generate a magnetic field, a planet needs a hot, swirling core. A dead interior should mean zero magnetism. Yet this wireframe shows what Voyager actually measured. Uranus has a massive magnetic field, but its axis is offset by a third of its radius and tilted at a 60-degree angle. Because of this misalignment, the magnetic field wobbles in a chaotic corkscrew motion as it rotates. To explain how a cold core could pull this off, we have to look at the planet's composition. Deep inside this ice giant, pressure compresses water and ammonia into a dense liquid slush that can reach 5,000 degrees Celsius. As this electrically conductive slush churns around, it generates the massive magnetic field. But while that solves one mystery, it leads directly into the final contradiction of the mission. Voyager detected electron radiation belts around the planet, so intense they were second only to Jupiter's. To sustain radiation belts of that magnitude, a planet needs a constant supply of particles. They get this fuel from plasma floating in the magnetosphere. But when Voyager measured Uranus's magnetosphere, it found almost zero plasma. There was nothing there to feed the belts. Discovering supercharged radiation belts with no plasma fuel is like finding a raging forest fire with no wood to burn. The measurements didn't match any existing scientific model. That contradiction sat in the archives for nearly 4 decades. It wasn't until 2024 that scientists reanalyzed the raw data to see if we had missed a variable. They found the missing piece. On the exact day Voyager arrived, Uranus was struck by a rare, unusually massive burst of solar wind. The force of the solar wind crushed Uranus's magnetic shield down to just 20